Hi, Robert. I'm Ross. I'm going to help you walk through this derivative problem. Tell you right now, it's a lot of work. There's a lot of steps that go into this, but I'll do my best to explain them. It all hinges on, for part A at least, the formula, which is sometimes called the definition of a derivative. So for any function f, right, you can find f prime, the derivative, using this limit. The limit as h approaches 0 of f of x plus h minus f of x, all divided by h. So keep in mind, sometimes this throws people, what we're really saying there, this x plus h is our input. So all that means is wherever we see an x in our function, we're going to replace that with x plus h instead. And then h is just a variable that eventually will replace with 0, but that'll happen later on. So I'm going to go ahead and jump into this. A lot of work involved. So we're going to start out. First of all, don't forget as we're working to keep your limit as h approaches 0 and your denominator of h around. A lot of times those get forgotten. So don't forget those. And all we're really going to be doing for the first several steps is working with this numerator. So let's jump into that. So f of x plus h, like I said, we're going to replace our x here with x plus h. And so that'll look like 1 over 3 times, instead of x, it'll be x plus h, and then plus 1. So that is just this first term. And then minus f of x, which is just the function, the same old function we started with, nothing different about it. Okay, that's the very first most important step. We've used this function, we've applied it to, or this limit, we've applied it to our function, but now we've got a lot of algebra to do. And so I'm going to go ahead and get to work on that. And the first thing I'm going to do is I'm going to multiply out some of this, these denominators just to clean it up a little bit, this first one in particular. So I'm going to rewrite this limit of h approaches 0. I'm going to distribute down here, so this will become 1 over 3x plus 3h plus 1. And you don't have to take that step, but it just makes it a little easier to look at later on, I think. And then 1 over 3x plus 1 doesn't change. And then don't forget your h, everything's over h. Also, quick side note, if you're wondering, like, why don't we just go ahead and plug in h, 0 for h, if that's what we're going to do later? If you tried to do this right now, you'd get an undefined value. So in a little while, once we kept doing several more steps, you'll see that there's a trick to this that keeps us from getting undefined. So let's keep going. We've got to deal now with the fact that in the numerator, we have actually two different fractions. We have two fractions inside of a bigger fraction. And so what we want to do is combine those two fractions into one. To do that, we need a common denominator. And there's a really common strategy for doing that. I'm going to bring this over to the side here and do this separately just to kind of clear things up. So I have 1 over 3x plus 3h plus 1, and then minus 1 over 3x plus 1. Please excuse the terrible handwriting. All right, so I want to put those together. The quickest way to do that, and a really common strategy, is to multiply each fraction by the other denominator. So the second fraction, for example, I would multiply by the first denominator, 3x plus 3h plus 1. And don't forget to keep everything equivalent. We've got to do that on top and bottom. So 3x plus 3h plus 1 down here. And then the first fraction, we're going to multiply by the second denominator. So the top and bottom, numerator and denominator, will get multiplied by 3x plus 1. And 3x plus 1 down here. Now keep in mind that because we did that, I've got a 3x plus 1 and a 3x plus 1 over here, 3x plus 3h plus 1, 3x plus 3h plus 1. We've automatically now got a common denominator. So we can put those two fractions together. And that common denominator is going to be, and I'm not going to multiply it out because it'll just make our lives harder later. It's just going to be 3x plus 1 times 3x plus 3h plus 1. So that part's easy. The numerators is where it gets a little trickier. So let's go ahead and do that part. For this first one, I have 3x plus 1 times 1, which is just going to be 3x plus 1. And then over here we have minus. So be careful with that. That minus needs to get applied to everything else. So I'm going to put parentheses around this. And then 1 times the rest of this is just going to be the rest of it. So 3x plus 3h plus 1. So great, we've combined the fractions. Now we can just clean up the top a little bit by distributing our negative and combining like terms. So that's going to be, when we distribute the negative on top, we're going to have 3x plus 1, just like we do up here, minus 3x minus 3h minus 1. Now, hopefully you can already notice that something cool is going to happen. The bottom will not change, 3x plus 1. It could, you could distribute, but don't. It'll make your life harder. So the bottom stays the same. And hopefully you've already noticed that the numerator, in the numerator, we're actually now going to be able to cancel the 3x's and the 1's. So the only thing left in the denominator is going to be negative 3h, which you'll see in a second is going to be super convenient. So now that all that's done, I'm going to bring it back over here to our limit. Told you it's a lot of steps. And so what we have is the limit as h approaches 0 of negative 3h divided by all of that crazy denominator, 3x plus 1 times 3x plus 3h plus 1. And then don't forget that all needs to get divided by h because of our limit. Now, this I think is one of the least intuitive steps. We're going to take this fraction and kind of flip it. So consider it this way. When we have two fractions, for example, if I have 1/2 divided by 3/4, when you divide a fraction, you flip it and multiply. So this would be equivalent to 1/2 times 4/3. We're going to use that same idea by looking at this h. Instead of just h by itself, we're going to think about it as h divided by 1. Anything can be a fraction if you just divide it by 1. And so we're going to apply that same idea about dividing fractions. Give myself some room here. And we're going to turn this into the limit as h approaches 0. That doesn't look like an m. Of negative 3h over the whole denominator. That first fraction doesn't change. Times 3x plus 3h plus 1. And then that's all going to get multiplied instead of h over 1 times 1 over h. Now this is the most important part of the problem. It's why we went through this whole thing. Earlier I mentioned, right, h needs to get plugged, or sorry, 0 needs to get plugged in for h at some point. But I told you that can't happen over here, right? It'll give you a undefined value. Watch what happens now. Look at the top of this first fraction. We have an h. And on the bottom of the second fraction, we have another h. So those will cancel. Now we're going to go back and try and plug in the 0 for h. And let's see what we get. So I'm going to rewrite my limit. The limit, actually I'm not going to rewrite my limit because we're plugging in the 0. As soon as you plug in the 0, the limit disappears. So I'm just going to go ahead and write what's left. That h is gone. Negative 3 times 1 on top is just negative 3. And then on bottom, notice we're not plugging anything into x, right? We don't know what x is yet. We just know h needs to be 0. So on bottom, I'm going to have 3x plus 1, again, times 3x plus 1. And if you're wondering where that came from, what I've done is over here, if we plug in 0 for this h, 0 times 3 is 0, and all we're left with is the 3x plus 1. So this expression is what we end up with. All of that work gets us down to this expression, which is our derivative. When you follow this process, your ultimate goal is to get rid of h, eventually plug in 0 for h, and see what you end up with. And once that's done, you've got your derivative. Now I'm going to rewrite this just a little bit to make it a little bit more common. We would write f prime of x equals negative 3 divided by, and you could rewrite the bottom there as 3x plus 1 quantity squared. So finally, all that work and we've got our derivative. It took almost 10 minutes. Now, if we go back, what we actually wanted to know was f prime of 4. All we got to do that to find that is plug in 4 to this function. And when you do that, you're going to get -3 over 169, which is some weird decimal, but that's the answer. So all that work to get a derivative just for the final answer to pop up in a matter of seconds. So using a limit to find a derivative is a ton of work. It can be. Sometimes it is super, super easy. Sometimes it is a lot more difficult. In part B, I do want to show you. So it said for part B to find the derivative, find f prime of 4 using formulas. I assume they're talking about like the quotient rule or the power rule. I'm going to show you the quotient rule really quickly. So we are going all the way back to our original function, which is 1 over 3x plus 1. I'm going to use the quotient rule to find the derivative. So f prime of x would be the denominator, 3x plus 1, times the derivative of the numerator. The derivative of 1 is 0. So that will all actually cancel, convenient, minus the numerator times the derivative of the denominator. The derivative of the denominator is just 3. And then that should all get divided by the denominator squared, which honestly is kind of annoying because look at what we got. -3 divided by 3x plus 1 squared. And in about like a 10% or less of the time. So knowing how to use that limit is really important. It's really important conceptually so that you know how to do it. But a lot of times using derivative rules, formulas, and things like that is way faster and sometimes more valuable. Regardless, I hope that helps you to understand what's going on there, understand how these problems work, and hopefully tackle some additional problems on your own.